Hello dear students, my name is SURAJ PRASAD and I am working here in Sri Chaitanya campus as a chemistry senior lecturer. Today we will be talking about a very important chapter, electrochemistry, and in that we have taken a portion electrochemical cells, which is the beginning of the electrochemistry. Now it is very important to know about the electrochemical cells because that will give us the way how to think in this chapter. So first of all, I will be telling you about the various composition of a electrochemical cell, or what do you first mean by electrochemical cell, and then I will be going through the equations, how to deal with the calculation stuff. So here we go. This you can see an image I have taken and you can see that there is something called some electrode, some electrolytes, okay, and bulb is glowing on. So like this we will understand that what is actually happening and here you can see that some part which in our this session you will be able to understand completely. So again we will come back to this image and then I will ask you that what was there in these parts. This is basically a galvanic cell. So first of all, electrochemical cells. How do I define the electrochemical cells? So an electrochemical cell is a device that can generate electrical energy from the chemical reactions occurring in it. Well, when we talk about the chemical reaction occurring in it, then we are actually saying that redox reactions happens here. Means here oxidation and reduction processes, they takes place simultaneously by connecting the system, and that is called redox reaction. So one side will be called as oxidation half cell and one side will be called as reduction half cell, which will be joined, and there will be a connection more which is called short bridge connection internally. We will talk about it. So reactions occurring in it, or it is also the use of electrical energy supplied to it to facilitate the chemical reaction in it, which is the second part, which is called the electrolytic cells. When we do for the Faraday's law of electrolysis, then there we talk about the electrolytic cells. What do we do there? We provide the electricity and then some chemical reaction occurs at either the anode or the cathode side. So there is two types of cells, I would say. One is called galvanic cells, where we have chemical reaction converting to the electrical energy, and second type cells is called electrolytic cells, where electricity is passed and then anode and cathode, some things are getting deposited, some gas is getting liberated, like that the things are happening. So that is how we have to proceed in these particular cells. Now let's talk about the common example. So the common example of an electrochemical cell, which I am talking right now here is a galvanic cell, is a standard 1.5 volt cell which is used to power many electrical appliances like TV remotes and clocks. You might have seen that small cell which is of 1.5 volts, 1.2 volts, 1.1 volts available in the market, not very costly, 10 rupees, 20 rupees, 15 rupees, okay, and it runs for a lot of time, maybe for 3 months, 4 months, at least 3-4 months. Those batteries they run in a TV remote or a clock, wall clock. So they are what? They are electrochemical cells only. There, what is happening? There the chemical energy is getting converted into the electrical energy. So that is the application part of it. So that is an example. Then such cells which are capable of generating an electric current from the chemical reaction occurring in them are called as galvanic cell or voltaic cell. So because Alessandro Volta was the person involved there, so that is how voltaic cell, and Luigi Galvani was involved, so galvanic cell. The names are coming from the scientist name. So it is again the same thing which we have discussed, that chemical energy will give me electrical energy, and the cells are called galvanic cells and the voltaic cells based on the scientist name, Alessandro Volta and Luigi Galvani. They were the scientists who has found these cells. Alternatively, the cells which cause chemical reactions to occur in them, which is like the second part which I told you, when an electric current is passed through them, they are called electrolytic cell. So two types of cells are there. One is your galvanic or voltaic cell, and one is your electrolytic cell, as I just told you before. So this is the definition part. Now in this image, I hope you are able to see this image a bit clearly. It is a bit hazy, but things which you have to note is like there are two halves. One is oxidation is going on, so this will be called oxidation half, and here the reduction is going on, so this is called reduction half. Now here the metallic rods which are used, these are called what? These are called electrodes. Electrodes are of metals generally. Even non-metals which are conductors, like carbon electrodes also we take, graphite ones. So the conducting materials, basically we take it as electrodes, from which or via which the electrons can show the movement, and there can be a movement of the electrons. So you can see here, this is a very basic example of a voltaic cell and a galvanic cell, where what is happening, electrons from this electrode, zinc, can you see zinc? From zinc it is moving to the copper. So in generally in the electrochemical cells, the electrons they move from the anode side to the cathode side, and this happens how? This happens because the anode side oxidation takes place. Oxidation means loss of electron. So here zinc is losing the electron, forming Zn2 plus, and that electron is getting collected by the wires, and the bulb, you can see it is glowing. Similarly, in the cathodic side, if you will see, copper is used. So this is the voltaic cell we are talking about. In that zinc and copper was used, and the cell potential was how much? Cell potential was 1.1 volts. Okay. So the copper is getting reduced actually. Here what reaction is occurring? Here the Cu2 plus, the ion, that is accepting the electron to form the copper. So copper is getting deposited here, but here Zn2 plus ions is formed in the media, in the solution. So there are two things over here. Two electrodes are there, one at the anode side, one at the cathode side. Then electrolytic solution is also there. So copper sulfate is blue in color, that is why it is blue, you can see, and that is a bit silver grayish in color, zinc sulfate. So this is your ZnSO4 and this is your CuSO4. Colors also you can detect, because you should know the color. So this is your copper sulfate. And one more thing which is important is the salt bridge. Can you see this internal connection? This is called salt bridge, means outer side it is connected by a wire, but inner side it is connected by a salt bridge. This is called internal connection. The circuit is complete, the internal circuit is complete. Okay. And also the salt bridge role is what? If suppose salt bridge is not there, if we simply connect by some glass tube or just complete the internal circuit, then what will happen? All these phenomena will learn in the further slides. So this is the basic diagram, and you have understood that what is the composition of a electrochemical cell, basically the voltaic cell or the galvanic cell. So composition is that electrodes are there, electrolytes are there, then for external circuit completion wires are there, and for internal circuit completion salt bridge is there. The salt bridge which is mentioned here is KCl. Generally KCl is taken because it depends upon the movement, the mobility. So the K plus ions and the Cl minus ions, they have nearly the same mobility, so they will not allow the liquid-liquid junction potential to happen. And a salt bridge is used for what? It is used to avoid the liquid-liquid junction potential. The cell is protected, otherwise what will happen? It will be generating a reverse direction and our cell will be of no use. So we will talk about it, that how the junction potential get developed. Salt bridge happens to nullify the things. The positive ion K plus will be going to the the negative solution, and Cl minus will come here in the Zn2 plus solution. So we will see that. So galvanic cell, the image, the video we have just seen, again I am repeating, cells which are capable of generating the electric current from the chemical reactions occurring in them are called galvanic cells or voltaic cells. I told you the reason also based on the scientist name they are. Then redox reaction takes place at both the sides of the cell electrodes. One is called oxidation half cell, one is called reduction half cell, and then they are connected. So it is a simultaneous oxidation and reduction. The process is called redox reaction. So oxidation, it takes place where? You have to remember, it takes place at the anode, and reduction takes place where? Reduction takes place at the cathode. Generally, anode is our negative terminal, and from there the electrons flow from the to the cathode side. There is a trick to remember also. Some people may confuse between the anode, cathode, negative, positive and all, and where it is written left hand side, right hand side. So there is a trick. Please remember that trick. It is a very famous trick, loan. Okay. I know that you people are very rich, so you do not need any loan, but I was so very poor at my time. So I had taken student loan also and various loans right now also. So loan concept is used here. L means left, O means oxidation, A means anode, and N means negative. So now I hope it completes your all the things of which side oxidation is taking place, what that is called, positive, negative it is. So left oxidation, anode, negative, lone. If left is obviously anode, the right would be what ray? Right would be cathode. Okay. So that you have to yourself judge by the help of common sense. Then the third thing which I just said, that outer connection is completed. Okay. From the anode side to the cathode side, the outer connection is connected, but the internally how it is connected? So for internal connection we require salt bridge, and for salt bridge the material which is generally used is KCl. You can use another material also, like some cases KNO3 is also used, some cases Na2SO4 is also used, but generally KCl, because of the material should be used so that both the ions should have nearly same mobilities, so that it will nullify from both the sides the extra ions getting produced in the electrolytic that solution. Okay, so suppose at one side we have more positive ions, one side we have more negative ions. If they will come together, if they will come close, what will happen? A reverse potential will get generated because of the potential difference, plus and minus charges. So that is called liquid-liquid junction potential, and the direction of it is just reverse of the cell potential. So what will happen? Our cell will be not working. After some time, your cell will be like dead. So to protect our cell, what do we use? We use salt bridge, which will nullify the effects of the extra accumulation of the positive charges or the negative charges, and that is how our cell keep on working till our electrode material is there. So salt bridge it is used, and substance like KCl is used to protect the cell from liquid-liquid junction potential, which is reverse in direction to the cell current. Okay. So it is very important, otherwise the cell will be not in the working condition. Now this is a diagram of the galvanic cell, again voltaic cell, and I have written here the reactions also. Can you see the reactions? What is happening over here? Zn is converted into the Zn2 plus. So that means zinc from here Zn is getting converted and forming Zn2 plus. And rest what is happening? Electron will be there. So electron will travel this path, and from the wires these electrons will be connected to the cathodic side. And what is happening over here on the right hand side? Reduction happens. I told you left hand side oxidation will be happening, and right hand side reduction will be happening. So right hand side, yes, reduction is happening. Cu2 plus is accepting the electron, forming the copper metal, means copper is getting more deposited over here, and here your the electrons, the copper is accepting, like Cu2 plus, this is accepting the electrons, 2 electrons to form the copper. So slowly what will happen? Its mass will also increase, the electrode mass will also get increased, and you can be asked the questions also, like what is the change in the mass if they are giving some conditions regarding it. So this is the basic outer circuit, and voltmeter is used. You can see that there will be deflection in the voltmeter whenever we have the current flow there. So this is the normal outer connection, and here you can see the salt bridge. Now you see what is going to happen here. If Zn2 plus is more, that means this side your plus signs is going to be more in the solution, okay, as compared to the negative ions. The plus signs is going to be more in the solution. And this side, what is going to happen? This side Cu2 plus is depositing on the Cu. That means the anions, sulfate ions, SO4 2-, so negative ions will get accumulated. Now what will happen, Ray? What will happen if you simply connect it by any glass tube, okay, for the internal connection, then the plus and minus, the potential difference will be there because of the two accumulation of the charges, and this potential is just opposite to the direction of the current. Here you can see electron is flowing in this direction. So what is the current direction? Current direction in this direction, okay, from the cathode to the anode. This is the electron flow direction. We know that the current direction is opposite of the electron flow direction. So if this is the direction of the electron, obviously this will be the direction of the current flow, and here you can see that plus is here, minus is here, so this direction will be just opposite of the above one of the current direction, and that is what we have to protect. We don't want to accumulate these ions, and KCl, the KCl which we are using, this will protect our liquid-liquid junction potential and save our cell. How it will protect? The Cl minus from here, it will move this side, and the K plus from here, it will move this side, and they will balance the ions. They will not allow the accumulation of more ions, so that the potential will not be generated. So if the potential is not generated, then obviously this is simplified, and our cell will simply keep on working like this way, because there is no reverse potential like junction potential. So salt bridge, very, very important. Many times theory questions comes of salt bridge, okay, that what will happen if salt bridge is not used, okay, what do salt bridge function, which material we can use in the salt bridge. So please remember, in salt bridge we will use the material which have the nearly same mobilities like KCl. Then salt bridge will protect the cell, because it will not allow the liquid-liquid junction potential to overcome our cell potential, because the direction otherwise will be getting totally cancelled and our cell will not work. So it protects the cell from the liquid-liquid junction potential. So this is what we have read all about the copper and the zinc cell and how to represent the cell. This is what at the end, can you see, it is called cell representation. It is called cell representation. So on the left hand side you will be writing the anode thing. So obviously zinc is there, converting to the Zn2 plus. So zinc Zn by Zn2 plus means ZnSO4 aqueous solution. If concentration is given, then we write the concentration also, and we write a slash whenever there is a phase difference. So obviously the zinc here in the solid phase and this is in the aqueous phase, so we will write a slash. After that what we will do? We will do the salt bridge. This double line, double slash which you are seeing, this is nothing but the salt bridge, okay. After salt bridge writing, we will write the cathodic side. So this is your CuSO4 aqueous side by Cu, means Cu2 plus is converting to the Cu, cathode side, okay. So this is the reaction, because Cu2 plus is converting to Cu, so obviously we will write the Cu2 plus here to converting to Cu, and here Zn is converting to the Zn2 plus. So that is what we are writing here, Zn to the Zn2 plus. And they both are connected by what? They both are connected by salt bridge. Salt bridge is represented by double line, okay, double slash. So this is the full picture of a basic cell. Now we will also understand how to calculate the EMF of the cell, okay. Like if I tell you the exact values, the E naught of this is your 0.34, and for this E naught is 0.76, okay. And when we when we calculate the total cell potential, it will come out to be 1.1 because we have to add the E oxidation and the E reduction. So this is the, I have written E reduction and E oxidation value. So this is the E reduction value and this is the E oxidation value, and there is a formula of cell potential that E cell will be equal to oxidation plus reduction, E naught oxidation and E naught reduction. So by that we will see that if we will add, then the E naught cell of a galvanic cell, it comes out to be 1.1 volts. It comes out to be 1.1 volts. What is the formula? The formula is E naught cell. E naught means standard EMF at standard conditions. Temperature 25 degrees Celsius and pressure is 1 bar. So E naught cell will be equal to E naught of oxidation plus E naught of reduction. If we are writing only in terms of reduction, then you have to convert the oxidation and the sign will be changed. So minus will come. We will see in the next slide. See, this is the calculation of the cell potential. Formula is E naught cell is equal to E naught cathode minus E naught anode. Please remember this formula. In this one, I just told you that generally it is E oxidation plus E reduction. But when you are writing only with respect to oxidation or only with respect to reduction, then one of the quantity you have to do the polarity change. So the formula which is given here is E naught cathode minus E naught anode. That means for cathode though it is okay, but anode it is taking the minus sign. That means it is not taking the oxidation potential, it is taking the reduction potential of the anode. So this formula is used for the cell potential calculation, but please remember that this is also your RP and this is also your RP. These both are reduction potentials. These both are reduction potential. If suppose it is a oxidation potential, then plus sign will come here. E naught of the, because at cathode reduction is happening, at anode oxidation is happening. So if this is taking as a positive, this is taking as a reduction potential, but obviously reduction potential plus oxidation potential should be our answer. So if it is using the minus sign, then it might have used the reduction potential value, it has not used the oxidation potential value. What is the relation between reduction potential and oxidation potential? Of the same equation, just reverse it. So the sign will also change. For example, like for zinc, if I am writing, when I have written Zn convert to the Zn2 plus 2 electron, then this E naught will be called as E naught oxidation potential. OP will be called. This E naught will be called oxidation potential. How do we write the RP of that particular equation? Just change the equation. It will become Zn2 plus 2 electron. It gives Zn, and for this, what will be the potential? Obviously, suppose it is X here. So here the E naught will be equal to minus X, right? E naught will be equal to minus X, which will be taken as a reduction potential. So I hope you understood that here they are just changing the value to the RP, that is why minus sign is used. If they would have taken the OP value, then plus will be used simply because E naught cell is E oxidation plus E reduction, cathode plus anode, when we are taking the reduction of the cathode and oxidation of the anode. But if we are talking only in terms of RP, then obviously one of the sign will be getting negative. If only in terms of OP, then this will be positive and this will be negative, then we will say E naught of anode minus E naught of cathode in terms of OP. So I would say that better not be confused. Remember with one formula only and write it this formula. E naught cell is equal to E naught cathode minus E naught anode, and we have to write the E naught RP, reduction potential. We don't have to write the OP. We have to use only the RP. Okay. So this is how we calculate the cell, and like that only we have calculated 1.1 volts for the galvanic cell. Now this is a very important equation, Nernst equation, very important, because by the help of this standard EMF, so we can find by the normal values which is given in the table and all, but this equation will tell you that at any temperature, at any condition, what is the cell potential. So Nernst equation is helpful for calculation of our E cell, okay, at any other condition than the standard condition. Because if it is a standard condition, then we use E naught. But at other condition, how to calculate? We will use Nernst equation. So how Nernst equation comes? It comes from the thermodynamic equation. Delta G is equal to delta G naught plus RT ln Q. What is Q? Q is called reaction quotient. Q is called reaction quotient. I hope in the 11th class you have read well the equilibrium chapter or the chemical equilibrium or the ionic equilibrium chapter, right? Where you have studied about the reaction quotient. So like if I write AA plus BB gives CC plus DD, then we write Q as C power C, D power D by A power A, B power B, like this, correct? So this is your reaction quotient, and if those concentrations are at the time of equilibrium, then it is called equilibrium constant, Kc. So if they are at any time T, then it is reaction quotient, but if they are at the time of equilibrium, then it is called as equilibrium constant, Kc. And I hope you remember Kc, Kp calculations also. Okay. So then we just open it, delta G is equal to minus NFE. So delta G is minus NFE is equal to minus NFE naught, because naught is there, plus RT ln Q, log Q, okay, natural log. And from here you will get this equation that E cell is equal to E naught cell minus RT by NF. What is N over here? N is the number of moles of electron transferred in that particular reaction, in the redox reaction. Okay. Suppose in the galvanic cell, what is the N? In the galvanic cell, if you write the net cell reaction, what it will come? Zn is converting to the Zn2 plus 2 electron, and copper is converting to the Cu2 plus 2 electron is converting to the Cu. So what is the net cell reaction? Net cell reaction will be Zn plus Cu2 plus gives Zn2 plus Cu. This is the net cell reaction, and the total electrons involved in this redox reaction was 2. So here the N value is how much? N value is 2. What is the Q value for this? Q value will be equal to the Zn2 plus concentration, okay, power 1. This is the solid form, so I will not write the concentration here, divided by, this is also pure solid form, okay, so I will take it as unity. Only here I will write the Cu2 plus concentration. So this is the reaction quotient for that particular equation, galvanic cell, which we have discussed. Okay. So, and also remember that this equation is important, but many times they will give you the temperature. They will ask you at 298 Kelvin, 25 degrees Celsius. So after putting the value of R, after putting the value of T, after putting the value of F means farads, and 96750 as a like approximate value. After putting all these value over here and also converting the natural log to the 10 base log, how do we convert natural log to the 10 base log? By multiplying by 2.303. By multiplying by 2.303. So after substituting all the values at 298 Kelvin, the E cell is equal to E naught cell minus 0.059 by N log Q. So this log is what? This log is 10 base log, and it is very, very important formula, because many times you don't need to do this all calculations, it will be time waste. So if temperature is mentioned 25 degrees Celsius, directly we will do 0.059 upon N log Q. So which means what? Which means that you should remember directly this formula. E cell, any cell, if we want to calculate, it will be equal to E naught of the cell, means standard EMF first of all we will calculate, minus 0.059 upon N, 591 also sometimes it is used, log 10 based Q. This is the basic formula, but at what condition? This is only at 25 degrees Celsius, 298 Kelvin. Please remember, it is very, very important, because if you use it in any other temperature, then obviously the answer will be wrong. So temperature is a very important aspect. So please keep in mind that this is only applicable at 25 degrees Celsius. And many people, they learn this formula, but they do not know the validity that no, it is only applicable at 25 degrees Celsius. So please remember this. Now from here, one more thing I want to tell you that sometimes the question can ask you equilibrium constant calculation also. They will ask you that what is equilibrium constant. So how we will find the equilibrium constant? It is like at equilibrium. At equilibrium, what happens, do you know? At equilibrium, the rate becomes equal, right? And what happens if the rate becomes equal? The rate of the transferring of the electron or gaining of the electron, they will also become same. So we will say at equilibrium, what is going to happen? At equilibrium, your E cell will be equal to 0. E cell is equal to 0. Delta G is equal to 0. Okay, these all things will going to happen at the time of equilibrium. And if this is 0, we'll put here the value. So 0 will be equal to E naught of the cell, means standard EMF of the cell, minus 0.059 upon n log 10 base. Now students, please take care. Now your Q will become what? Your Q will become K, because we are calculating at equilibrium. So log 10 base K, K or Kc. So from here you get a formula of E naught cell and your equilibrium constant. So E naught cell will be equal to 0.0591 upon n log 10 K, and from here we have to calculate, we have to take the anti-log and get the value of equilibrium constant done. So this is what we have discussed today in this class, in this session. Okay, just go through again the slides what we have covered. First of all, now I hope you are able to understand this diagram which I said in the beginning, that there is something called electrodes, electrolytes, and see Zn is converting to Zn2 plus, Cu2 plus is going inside, so that means more ions, anions will be here, sulfate, so anionic flow can happen. This is what, this is your liquid-liquid junction potential will happen if I connect them directly. Okay, to avoid this condition, what they use salt bridge, in which for neutralization they use the instruments, substance, and I hope it is clear. Then we have seen the definition of the electrochemical and the electrolytic cells, and now I hope you can imagine that how Cl minus is going this side and K plus is going this side and neutralizing the effects. Okay, neutralizing the effects of for the liquid-liquid junction potential. Then again the definition and some points we have discussed. Then totally I told you that how to read a cell, what are the representation of a cell. So this also you should remember. Formula, many students may get confused, but please remember that here also I have told you the formula, that basic formula is E naught of oxidation plus E naught of reduction, which means what? Which means the E naught of cathode plus E naught of anode when we are talking of the E naught oxidation, and cathode when we are talking of E naught reduction. Okay, or should I, one second. Otherwise you will get confused. For oxidation we have a anode, and for reduction we have cathode. So when those equations will be used, then directly we will be using their addition directly. Okay, the E naught value directly. Like here I told you the E naught value is this, so this is what oxidation. Here I told you E naught value is this is what reduction value. So we can add both this value and the answer is 1.1 voltage. But if you are using with respect to one as both as like Rp, then the formula will be cathode minus anode, because one we have to change. This we were taking oxidation potential, we will change it to the reaction potential, so minus sign will come, and that is how the example I have taken, that sign also changes if you change the OP to the RP. And then we have discussed the Nernst equation. Nernst equation tells what? It tells us to do the calculation, to do the E cell calculation, means cell potential at any other condition than the standard EMF conditions. and from here we can find the equilibrium constant value also. So that is what we have done in this class. A very big thank you for all of you to listen to it, and I hope your concept regarding the electrochemical cells might have been now improved, and now just try to attempt the questions which will help you out. Concept is clear, but only concept will not help, questions will help. So please do a lot of questions on it. The more you will be doing the pen and paper practice, the more you will get the confidence, and it is game of confidence only. So please do a lot of questions. Please try to solve the previous year questions, module questions, all questions. That's it for today. Thank you.